All right, this problem has us deal with a heat pump and a refrigerator. So part of this is just to kind of familiarize you with working with those two systems. And I want to remind you what they have in common with the heat pump. So actually the first line of this problem says that we have an engine and that engine is run in reverse as a heat pump. So remember that all we need in order to create a heat engine is a hot and cold reservoir. So I have those represented here. Now, if we run it as a heat engine, then what we're doing is we're taking advantage of the fact that in our universe, there is a spontaneous heat flow from hot to cold, right? And we take advantage of that spontaneous heat flow. I say spontaneous, meaning that happens on its own. There's nothing that we need to do to make that happen, right? That's part of second law, is that some of the characteristics of our universe are that there's spontaneous heat flow in one direction only, unidirectionally from hot to cold. So we take advantage of that spontaneous heat flow and we're able to create mechanical work out of that, right? So that's the heat engine that follows that pattern. Now, what they're saying is that let's take the same heat engine and we're going to run it backwards as a heat pump. So let's pause on this for a moment. What does a heat pump do? So a heat pump, I want you to think about it in a practical way. They're much more common in other parts of the world, or like say on the East Coast than they are out here on the West Coast. I guess, just doesn't get quite as cold out here. So how that would work would be like if you're familiar at all with like a window unit air conditioner, it would be kind of like turning that air conditioner around. If you've ever seen an air conditioner in a window, maybe you have, then you know that if you go outside while the air conditioner is running, there's hot air that's being pushed to the outside. And that makes some sense, right? You kind of think that, all right, well, you're cooling the space inside the house, so it makes sense that that has to go somewhere. So for a heat engine, I'm sorry, for a heat pump, think about rotating that 180 degrees such that that hot air is coming into the home. So a heat pump functions as heater for an interior space. So that heat's coming into the home. And what that means is that it's extracting energy from the cold temperature outside. And even though this is strange to people, like, well, how can you warm up your house if it's really cold outside? Um, we tend to be much more comfortable with the fact of an air conditioner. And that's in fact what an air conditioner is doing, right? So if the air conditioner is functioning in a building, say, the interior of that building is going to be a lot colder than the outside. But still, what that air conditioner is doing, right, to keep that temperature differential in place, is it is taking heat energy from the interior of the building and moving it outside. Okay, so when you think about a heat pump, it might help to think about it as an air conditioner kind of turned around. What that means is that you are saying that I'm forcing a heat transfer from cold to hot. So this is in the non-spontaneous direction. That doesn't happen for free. In order to force that to happen, now work needs to come into the situation. So now we need to add work to the situation. So, and like, as you know, you need to plug this thing in order for it to work. So that would be the engine run in reverse, meaning against the spontaneous direction. So we need to provide work in order to have it run that direction as a heat pump. Um, the second part of this first question says an identical engine with the same values of QH, QC, and W as the first engine is run in reverse as a refrigerator. So I don't have to change this diagram at all for a refrigerator. You just have to change your application concept of it, right? So for a refrigerator, QC is now the interior of the refrigerator. Yeah. And QH is like the kitchen or whatever space that the refrigerator is sitting in where it kicks out exhaust into. So if you are not familiar with that, go become more well acquainted maybe with your refrigerator and you'll be able to see that your refrigerator does actually exhaust into whatever room that you have it sitting in. Okay, so heat pump and refrigerator have very different contexts, right? For a refrigerator, you're cooling the enclosed space. And for a heat pump, you're heating the enclosed space. So if you need to diagram that out a little bit more for yourself, do that. You want to be familiar with heat engines, of course, heat pumps, and refrigerators, those as the three types of applied systems here. All right. So what this is telling us here is that the ratio, let's just write down what this problem is saying. The ratio of QH over W for the heat pump, I'll call that HP, is 3 times greater than the coefficient of performance of the refrigerator. So coefficient of the performance of the refrigerator, any of these like efficiency or performance coefficients, what these are about is always in the numerator goes the thing you want, the reason that you're building the machine, right? So the reason that you have the refrigerator is for the cold compartment. So QC goes in the numerator. And then in the denominator always goes what you have to pay to make that happen, like what has to go in. So a refrigerator, it's work, right? You got to plug the refrigerator in or it's not going to work real well. Um, so this is the coefficient of performance for a refrigerator. There's plenty about that in your textbook. So we know that for these different systems, the problem tells us that QH, QC, and W values are all the same between them, right? Those are all the same. So I can then write this equation out as QH over W equals 3 QC over W. I know the works are the same, so that tells me that QH is equal to 3 QC. This is super useful, and I can write this as QC is equal to 1/3 QH. So just kind of get your, get a handle on that for a moment. QC is equal to 1/3 of the QH. Okay, so by conservation of energy or first law, however you want to think about that, QH is equal to QC plus the work put in. And you can also see that in the diagram, right? If you look at these arrows here, what's flowing into QH here? Well, work's flowing in and QC is flowing in. So you can write your equation basically based on that. And nothing else that would be going on there. We just have those 3 components. So to sub in here, I can say, well, 3 sub in 3 QC for QH is equal to QC plus W. And that will give me this relationship, 2 QC equals work. QH, whoops, is equal to work plus, now what's my QC? QC, remember, is just QH over 3. So this renders me another relationship here. 2/3 QH is equal to work. So I'm just kind of taking these proportions, starting with this 1/3 and this other information here, and I'm able to write out some relationships just using a little bit of algebra here and first law, right? Putting those things together. So now this allows me to start solving or answering the questions that they want here. Question A, determine the coefficient of performance of the refrigerator. So remember, coefficient of performance for the refrigerator is equal to QC over work. And if I look at this now, what's QC over work going to give me? I can look at this relationship right here. QC divided by work is going to be equal to 1/2. Okay, so there's the coefficient of performance of the refrigerator. Part B asks me for the efficiency of the original engine. Right, so the original engine, now we have to remember what efficiency is. That's the thing we want to get out of the engine. So remember, work is what you want to get out of the engine, divided by what has to be put into the engine, which is QH. So I can get that relationship from this second algebraic manipulation here. Work over QH is equal to 2/3. So 2/3 is the efficiency of the original engine. And if we were to draw out the, just real quick, since I did the diagram for the heat pump and refrigerator, they would both be, this is the heat pump and then the refrigerator, right? They both could be represented by that diagram there. Let me really quickly diagram out You've probably seen this, but just in case, what our heat engine would look like. So there's my QH. For some of us, these diagrams are super useful. So for heat engine, of course, we've got this spontaneous heat flow this way that happens for free, and we get our work out. So I had that drawn in the beginning, but I just wanted to, this is the engine, to contrast with those.